Okay, so it is time. You get to be formally introduced to the definite integral. So in this section, we're going to move beyond finite sums, which are the rectangles, and explore what happens in the limit as terms become infinitely small and the number of rectangles approaches infinity. We'll look at some geometric functions that may contain negative values, shapes that are below the x-axis, as well as positive values above the x-axis and 0. So dealing with negative area, at times we are going to integrate functions that dip below the x-axis. And here are a few pointers for when that happens. Any area below the x-axis counts as negative area. The total area between A and B for some curve is really a net area, where the total area below the x-axis, which is above the curve, is subtracted from the total area above the x-axis, which is below the curve. So here's what that means. If I have a graph and it does that, this is all the area above, this is all the area below. So if I'm going from A to B, and I'm going to take, let's say, this area capital A and this area capital B. So the total area between A and B is going to be big A minus big B, because B is a negative area. So that's what it means by the net area. So you're not going to add A and B together, and B is not going to algebraically come out to be negative. You're going to have to remember that it's negative because it's below the x-axis. All right, definite integral notation. So here we go. Here's your little integral right there. This is what it looks like when you write him, like a weird S. From A to B, and I usually write my B on the upper left side, but type-wise, I think when it's typed, you're going to see that. Of f of x, and then it's always going to have a dx, and we're going to talk about that in a second. So this is how you read it. It is the definite, and I'll talk about why it's the word definite. The definite integral from A to B. So this is your smaller number and this is your bigger number, your left to your right. From A to B of f of x, and this is with respect to x because of the dx. Now it's a definite interval because it has, or integral, because it has the a and b. If you had an integral that looked like this is just the integral of f of x dx. It is not a definite integral because it doesn't have definite bounds. So a definite integral has from here to here. Let's see, this little b is called your upper limit. So that little a is your lower limit. There's your integral. This is called the integrand. And I don't use that word that much, but you may have some college professor that loves that word, and so I want you to know what that is. And then this is your variable of integration. And the whole thing is called your definite integral. The definite integral can be used to determine the net area or the displacement bounded by, okay, it's going to be bounded by the x-axis and the curve, and the curve is f of x, between the vertical lines, vertical lines x equals a and x equals b. So if I had some really cool curve and I was going from A to B, then I have these vertical lines that chop off. And I want that area, again, between the curve and the x-axis. And I want that area between the curve and the x-axis. But I want to stop here and stop here. Now, just eyeballing this, that area would be really close to 0 because it looks like I have just as much above the axis as I do below the axis. So that looks like it might be a little negative heavy, so I might have a little bit of a negative answer, but that one's going to be really close to 0. So when it says vertical lines, that's what it's talking about, from here to here. So it's like a bookend. All right. Oh my. Okay. So here we go. I have a graph of f of x. It is made up of all linear lines. And I want the value of the integral, and you need to be able to say it. I don't want to send you off to college going, you know, that squiggly thing. I want you to know that that is an integral. The integral from 0 to 7 of f of x dx. What is the value of the integral from 0 to 7 of f of x dx? So it's saying, what is the area of the curve from 0 to 7? So from 0 to 7. So I want all this area. Well, you don't know your integral rules yet, and I don't have a function. So I'm just going to divide this into shapes. So I see a shape there, and that's a rectangle or a square, yeah, and then a triangle, and then another triangle. Well, I know the area of a triangle is 1/2 base times height. The first shape is actually a trapezoid. Because my sides are different, it's not a triangle. I mean, you could make it into a triangle and a rectangle if you just really wanted to avoid a trapezoid, but I'm going to do a trap. So here's what I'm finding right now. I'm finding the area of him. So area of a trap is 1/2 height, b1 plus b2. So 1/2 and my height, which for us is the width, and then my base 1, which is 1, and my base 2, which is 2. 1/2 of 2 is 1, so that's a 3. He's a 3. The next one's a 2 by 2, so that's a 4. And this is a triangle, and triangle is 1/2 base times height. So 1/2, 1 times 2, so 1. Then this guy's also a triangle, 1/2 base times height. So 1/2 base is 2, height is 2. So 2, but he dips below the x-axis, so he's a -2. And you could look at this and say, well, his height is actually a -2, and that can help remind you that it's a -2. Although I don't see that happening. Well, maybe if it was a rectangle, you would look at the height as being a -2. I just remember that if it dips below the x-axis, it's a negative. So now I'm going to add them all up. 3 plus 4 is 7, plus 1 is 8, and 8 minus 2 is 6. I got A. So that is the area, the net area between the curve and the x-axis between the vertical lines of x equals 0 and x equals 7. You found all the area, the net area. All right, number 2. The graph of G shown below consists of the arcs of 2 quarter circles, so a fourth of a circle, and 2 straight line segments. The value of the integral of 0 to 12 of g of x dx. All right, so I want all the way to here. And I see a triangle. I'm just partitioning off my shapes. So I'm going to do the triangles first. 1/2 base, 1, 2, 3, times height. So 15/2. is that one. This one's 1/2 base times height, so -3 is that one. All right, quarter circle. Area of a circle is pi r squared, so a quarter circle would be that over 4. Radius here is a 4, so that would be 16 pi over 4, so 4 pi. And then this one, pi r squared over 4, 1, 2, 3. Radius is 3, so 9 pi over 4 negative. So let's see. If I have a 4 pi and a minus 9 pi over 4, well, that's 16 over 4. So 7 pi over 4 is going to be my pi part. And then I have a -3 and a 15 over 2, -6 over 2, which is 9 over 2. So B. This would definitely be calculator inactive. All right. Oh, I love these. Okay, so we have this really cool shape above and below the x-axis, and I have 1, 2, 3, 4, 5, 6, 12 questions about it. I want you to mark out L. Is that L? No, I. The F double prime of 6. Like, mark him out, not interested, just mark him out. So here's my challenge. Now that we've done number 2, I challenge you to pause me here and go do all 11 of these and then hit play and check yourself. So when I do these, I'm going to do them quickly because I'm going to assume you've already done them and you're just checking yourself. Okay? All right, everybody hit pause. All right. So first I'm going to start by sectioning off. So I got a triangle, I got a half circle, I've got a trap right there. I could go 2 triangles and a rectangle, but I'm going to leave it as a trap. And I got a trap below the x-axis there. So I'm going to just find all my pieces. So 1/2 base times height, so 4. Half a circle, so pi r squared over 2, and that would be the center. 1, 2, 3, so radius of 3, so 9 pi over 2, and he would be negative. Let's see, I bet, well, I don't know. All right, let's see. This whole thing is going to be a 1/2 height, base 1 plus base 2. So 1/2 height, and his height is 4. Base 1 is 7, and base 2 is 3. So 2 times 10, he's a 20. That's a trap like normal, not on its side. And this one's trap is below sea level, so 1/2. All right, its height 1, 2, 3, and base 1, 2, 3, 4, 5, 6. 1, 2, 3. So 9 times 3 is 27, so 27 over 2 negative. Okay, so I found my pieces. All right, let's give this a whirl. So this wants the integral from 0 to 7. So from 0 to 7, that's a 20. Technically unit squared. So unit squared for everybody, okay? From 0 to 13, so that's going to be a 20 and then a minus 27 over 2. That's 40 over 2. So 13 over 2. From -6 to 0. -6 all the way to 0, and that's going to be a -9 pi over 2. All right, now this one's interesting. From 3 to 3. So from 3 to 3. Well, there's no area there, so his area is a 0. So, and that's sort of a property rule. If you have the integral from a to a of something, it's always going to be 0 because you have no width. Okay, now let's look at this one. This one's going from 7 to 0, so that's backwards. So when it rolls backwards, you have to show that, and that's going to make that area negative. So from 7 to 0 is going to be -20. From 0 to 7 is +20. So if I roll backwards on a negative area, it would make it positive. All right, so now I'm going, oh my, from 10 to 4. Let me change colors. From 10 to 4. Okay, let me go from 10 to 7, and then let me go from 7 to 4. 10 to 7 is normally a negative area, but because I'm rolling backwards, it's going to make it positive. So I'm going to go ahead and put positive. And then from 7 to 4 is normally a positive area, but because I'm rolling backwards, that's going to make him negative. Okay, so now let's go find these values. So from 10 to 4, so that is a trap. So 1/2 and your height, 1, 2, 3. And your first base is 1, 2, 3, and your second base is a 2. So 5 times 3 is 15. So 15 over 2. And I made a note that it's positive, even though it's below, but I'm rolling backwards, so it kind of is like a double negative. And then from 7 to 4. So 1/2. All right, his height, 1, 2, 3, 4. And his base, 1, 2, 3. And his top is a 1, right? Yeah. So 2 times 4, that'd be 8. And he'd be negative. Nope. Hold on. Well, yeah, that's right. Yes, yes, I'm right. And then I add, so make that -16 over 2. So -1/2. If I add those two together. All right, good times. Now I want to go -8 to 13. I want the whole shebang. From -8 to 13, so we're rolling normal. So I've got a 4, a -9 pi over 2, a 20, and a -27 over 2. So 24 minus 36 pi over 2. So 24 minus 18 pi. Is that right? Nope, that's not right. Let's see what I do. (27/2). Oh, the 27/2 doesn't have a pi. Sorry, that's it. Sorry, I combined the two fractions, but I didn't realize that one had a pi and one didn't. That's my fault. So I have the 24 from these two, and then I need to minus the 27/2 because he also doesn't have a pi. So that's 48/2, which is 21/2 minus 9 pi over 2 because he has a pi. Okay, my bad. I want the derivative at -6. Does not exist. The derivative at -6 does not exist because that is a sharp turn. It changes from linear to a circle, and I can tell that that is not that the derivatives on either side of -6 would be the same. So no, that's a sharp turn. Does not exist. We're skipping. J wants the average rate of change. Okay, that's slope. I know what that is. That's slope in F from 0 to 5. Okay, so I need F of 5 and F of 0. Well, F of 5 is 4, and F of 0 is 0. So y minus y over x minus x. So 4 minus 0 over 5 minus 0 is 4/5. Okay, so here's what I did. I said, okay, 0, 0, and 5, 4. I went and found my points. True or false, from 0 to 2 plus 2 to 4 equals from 0 to 4. Yes, and I don't need to look at the graph to figure this out. The area from 0 to 2 plus the area from 2 to 4, and they connect, will equal the area from 0 to 4. 100% true. Over which values is f of x not differentiable? Okay, differentiable means I can take the derivative. So that's going to be anywhere I am not continuous or anywhere I have a sharp turn. So let's see. I don't like -6. I don't like 0 or 2 or 5 or 7 or 8 or 11. Yeah, I don't like any of those. Otherwise, looks good. Continuous everywhere, that's nice, but no sharp turn. So all those x values are out. All right. Accumulation functions. Given some function f of x is continuous function on a to b closed, shown below, suppose we define some function whose area under the curve between point A and some other point x. What? Suppose we define some function whose area under the curve between point A and some other point x. Okay, we can denote the area under the curve as a definite integral. Let's define this as a new function f of x, where x is in A to B. All right, so I've got this function whose area is from A to B. But now I want to define it as A to x. So I'm going to redefine this new function, capital F of x, from a same starting point to a new ending point, and I'm going to change it to f of t dt. So for any value x between a and b, this new function will give us the area under f of t between a and x. This is the fundamental theorem of calculus part 1 and helps us to make a connection between the integrals and derivatives, namely that every continuous function f of x has an antiderivative. That's all an integral is. It is the antiderivative. Remember I said half of calculus is going one way and the other half of calculus is going the other way? We are now going the other way. So we are antiderivatives, and that's all an integral is. So now, guys, anything that's called the fundamental theorem of calculus, that sounds pretty important. So let's love on this a little bit. Okay, lowercase f of x is continuous. Then I'm going to define some new function g of x. From a to some new value x, f of t dt, continuous on a to b, differentiable on a to b, also tells me that g prime equals f of x. All right, here's another way you can look at it. Alternative notation can be seen by taking the derivative of both sides of f of x. All right, look, guys, this is saying take the derivative of an integral. Well, they're opposites of each other. They cancel each other out. It's like squaring a square root. You're just left with the inside part. Now, don't get hung up on the T's and the X's, okay? Just trust me. Don't get hung up on that part. That's a very, very minor detail. I mean, it's important, but it's a very minor detail. This is what you're doing. You're taking the derivative of an integral. So you're saying if I have a 5 and then I subtract 5, I'm left with nothing. Or if I have a 5 and I multiply by 1/5, I'm left with a 1. I have undone. If I have the square root of x and I square it, I just have my x. Well, guys, if I take the derivative of an integral, I am just left with the inside part, the function that was in there. All right. We're skipping this part. Absolutely. Just trust me. No big deal. Let's look at the next part. Okay. Let f be the graph shown at the right. Okay, so we have this very linear function. It's got some area above, some area below. Okay, so capital G of x equals the integral from 0 to x of f of t. Now, f is the graph shown. Complete the table of values for g. So I want g of 0. Well, g is defined as the integral of f of t. So I'm going to start at 0 and I'm going to go to 0. Well, you know that that's going to give you an area of 0. I'm going from 0, I'm ending at 0, there's no area in there. Okay, now I want g of 1, so I'm going from 0 to 1. So I'm going to here. Well, the area, that's a rectangle. 2 times 1 is 2. So now I'm going to input a 2. So I want to find g of 2. Now look, they're trying to help us build this ourselves. So now I'm going from 0 to 2. Okay, well I know that's a 2. This is a trap. So 1/2. Now width is 1. And 2 plus 4. So he's a 3. So that would be a 5. And now I want 3, so I want g of 3. So I'm going from 0 to 3. This is a triangle. 1/2 base times height. He's a 2. So 4, 5, 6, 7. Now I'm headed to 6. So 0 to 6. Okay, we're now dipping below the x-axis. So that's going to be 1/2. His height is a 2. First base, 1, 2, 3. And 1. So 1, 4, negative. So 7 minus 4, he'd be a 3. Now I'm headed to 7. So that's a 1/2. 1 times 2, so that's a negative 1. So I've accumulated to a 3 so far. So if I add another negative 1 in there, that's going to bring me down to a 2. So this is an accumulation. I hope you guys see that. Like this, I'm starting from 0 to 0. Now I'm going from 0 to 1. Okay, now I want to go from 0 to 2. So all I'm doing is taking what I had and adding the new area to it. I'm accumulating. So now I've got the total area from 0 to 7. But if I add up all the individual pieces, the individual chunks, and add them all together, that gives me the total. It's an accumulation of values. Shown below is the graph of the derivative f for some function, capital F. Assume that f of negative 3 equals negative 8. Shown below is the graph of the derivative of f. The graph of the derivative f for some function, capital F. Assume that f of 3 equals negative 8. So at negative 3, I know that my area is already a negative 8. At -3, my area is already a -8. So I want f of 2. Well, that goes to here. So I have to add everything that's happened, everything up until 2. Well, I don't know what happens over here, but I know that once I get to -3, the total area is a -8. So if I know his total area is a -8, then to get the total area at 2, I'm just going to take -8, I'm going to add a 10 and a 26. So 28. So I did -8 plus 10 plus 26. So it's really important to make sure you understand what this means. All right, here's what this means. At x equals -3, my area has accumulated to a -8. You can't look at this and say, no, it's a -18. Well, no, that's only from -5 to -4 or to -3. That area is an 18. But this thing, all throughout its entire life, when it gets to -3, that total area is a -8. Its net area is a -8. I don't know what happens before -5. I don't know what happens over here. But them telling me this says, okay, at -3, I hereby declare that the total area that has accumulated is a -8. Now give me the area from basically -infinity to 2. Well, once I get to -3, I know that I'm a -8, and then I can just add the 10 and the 26. And that gives me my total area from -infinity basically to 2. So now I want to go to 6. Okay, let's see, 6 is here. So I'm going to have -8. That gets me to here. -8 plus 10 plus 26 minus, is that an 8? Yes. Minus 8 and then a plus 14. 16, 10, 20, 34. Okay, now what if I'm going backwards? All right. Here, the area that has accumulated is a -8. So that's the area from basically -infinity to -3 is a -8. I want the area to -5. So basically what it's saying is, all right, I want the area from -infinity to -5. So I don't want all of this -8. But I don't know what came before it. But I know the difference between the 3 and the -5 is a positive 18. So what I want to do with it is I want to take my starting point here, that's a -8, and I need to back 18 out of it. So that's going to give me a -26. So that I need to take 18 out of the total accumulated area that's gotten me to -3. I need to take 18 out of that -8 because I don't want it. I want to back up and give me the total area up to -5. All right, properties of definite integrals. These are super easy. The definition of the definite integral of f on the interval from a to b specifies that a has to be smaller than b. Now, however, it is convenient to extend the definition to cover cases in which a equals b or a happens to be bigger than b. And we've done both of those. So if f is defined at x equals a, then the area from a to a of f of x dx is 0. If f is integrable on the closed interval a to b, okay, then the integral from A to B, no, from B to A is negative A to B. And we did that. Well, I said, well, when you roll this way, it's going to make areas negative, or it's going to make negative areas positive. It's going to do the opposite. So we want to roll this way, from smaller to bigger. But when we roll from bigger to smaller, you have that negative on there because you're rolling the wrong way. Additive integral property, if f is integrable on 3 closed intervals determined by a, b, and c, then the integral from a to b, so the area from a to b equals the area from a to c plus c to b. Here's a, here's c, here's b. So the area from here to here is the same thing as the area from here to here plus the area from here to here. Parts, the sum of the parts equals the whole. If f and g are integrable and k is a constant, then, all right, so the integration of k times some function is the same thing as k times the integral of the function. In other words, you can take the constant out. This one is really important, and he kind of sneaks up on people. You don't see him that often, but you do see him enough to where if you don't remember him, it's going to hurt. So this is the integral from a to b of just a constant. So like the integral from 3 to 10 of 2 dx. So do you see how we have no variables? So I'm going to take my 2 and then I times it by the width of this. So 10 minus 3. It's almost, well, it's not almost, like it is. Remember, if you have 2, well, that's a flat line. So if I want the area from 3 to 10, well, guys, that's just a rectangle. So that's what you're doing. Here's your 2. That's your height. And then if I'm going from 3 to 10, well, if I subtract those, I get a 7. Well, that's an area of 14. So you're just finding the area of that rectangle. So it's the constant times the upper minus the lower. And that helps give you your width and keep it positive. If you have 2 separate functions, then you can write them as 2 separate integrals with addition and subtraction. Totally fine. Okay, so here we go. I have the integral of a to b of f of x dx is 8, g of x is negative 3, and h of x is 5 to 2. All of these are from a to b, a to b, a to b. All right, cool. So I want, a wants the integral from b to a of g of x. Well, that's a negative 3, and I'm rolling backwards, so that would make that a positive 3. B says twice, all right, I'm going from A to B, so that's normal, twice f of x, so that's just going to be 2 times 8, which is 16. I told y'all these were easy. This one wants the integral of 5 dx. Now, it doesn't have, I don't have an f of x, a g of x, or an h of x, so I don't know which function this is, so I can't find an actual answer, but there's my height, and then I'm just going to do upper minus lower. So it's going to be a rectangle, and that's going to be the value of the area. I just don't know what A and B are. All right, this one's going to be 2 separate integrals, so you can look at it like that. So 5 times B minus A for the first one, plus, and then G, A to B is a negative 3. F of x minus h of x, and again, you can look at this as 2 separate, a to b, so nothing funky there. So f of x is going to be an 8 minus 5 over 2, 16 over 2, so 11 over 2. Okay, so this one has h of x. He's going from A to 4, and he's going from 4 to B. So this one's going from A to 4. This one's picking up where he left off. So really, it's just the integral from A to B of h of x dx, which is 5 over 2. I love those. It's like a puzzle. Just watch your limits, your upper and your lower limits, and make sure they're not flipping them around on you. Okay. Oh, I love these. Given the integral from 1 to 3 x squared, 1 to 3 of x, 1 to 3 of a dx, so that's a constant, is 2, then find the integral from 1 to 3 of a negative x squared, so negative 26 over 3, plus 4x, so 4 times 4, 16, minus, all right, 3, which is going to be 3 times 3 minus 1, which should be 2. So negative 26 over 3 plus 16 minus 6, that's a 10. 30 over 3, so 4/3. Yep, I love those. Pause it, go back over it if you need to chew on it some more. Okay, number 3, I'm going from negative 5 to 2. Then I'm going from 5 to 2. Okay, that's backwards. Normally you would go from 2 to 5, and that was going from 5 to 2. And I want negative 5 to 5. Okay, negative 5 to 5. So I can do negative 5 to 5 by doing negative 5 to 2 plus 2 to 5. Like lower to upper, and then pick back up at 2 and head to 5. That'll get me from negative 5 to 5. So negative 5 to 2 is a negative 17. But 2 to 5, so that's backwards. So that would have to be a positive 4. So negative 13. So again, that's the sum of the parts equals the whole, going from negative 5 to 5. So I'm going to break it down to negative 5 to 2 and 2 to 5. Negative 5 to 2 was given to me plain as day. The other one was given to me backwards. It was 5 to 2, and I want to go 2 to 5, so I had to change the sign because I had to roll the other way. All right, 0 to 6, 3 to 6, then 3 to 0. Okay, mental note, he is backwards. So 0 to 3 would be positive 7. What is the value of, okay, 0 to 3, 0 to 3, oh, and this is G, these are F's. 1/2 f of x minus 3 g of x. Okay, I just want to go to 0 to 3. I don't have a 0 to 3. I have a 0 to 6 and a 3 to 6. So if I did this one minus this one, that would leave me with 0 to 3. So the first one gets me from 0 to 6. The second one takes me from 3 to 6. Well, I want this one. So if I do the big one minus the little one, that'll give me what I want. Okay, there you go. But I want 1/2, of course. I want 1/2. So first of all, I'm going to do 9 minus 5, and that gives me 4. So that's from 0 to 3, but I want to 1/2 it, so that's a 2. G of x, I want to do negative 3 times g of x from 0 to 3, that's backwards, so it's going to be a positive 7. So minus 21. So I got a negative 19. I love those. It's like a puzzle. I love it. And I know it's hard because I can't point stuff out. I can't read your face and see if you're getting it or not. So just if you're completely lost, start it, ask about it in class. But if it's just sort of not clicking, then just pause it, rewind it, go hear it again. But look at the pieces and think about, like I did here, think about a number line. Well, he gets me from 0 to 6, and he gets me from 3 to 6, but I want 0 to 3. So if I take the whole piece and minus the little piece, that'll give me the piece I want. So then I'm going to take this minus this. That's where the 4 came from. But then it wants me to half it, so I half it. All right. Number 5. Tell you what, pause me. Pause me and try number 5 on your own. Read what you have first. Okay, this is F and this is G, and this is from 2 to 6. This is 6 to 2, so he's backwards. So he 2 to 6 would be -7. All right, I want 2 to 6 of 3f of x, so 15, plus g of x from 2 to 6, and that would be a -7. That's an 8. Nice. Take time and read what you have first before you dive into these. Okay, number 6. Find the following. All right, tell you what. Ooh, this is a good one. Pause me. See what you can do. Let's see. 1 to 5 of 3 times f of x plus 4 is 34. I just want 1 to 5 of f of x. All right. Well, let's break him down into parts. So 3 times f of x is the same thing as 3 of fx. Okay, and I can look at him as a separate interval. 1 to 5 of 4. And that equals 34. And I want, oh yeah, here we go. I want him. So I'm going to treat this like an equation. So 3 times what I want, that's a 5 by the way. Now this one is a constant. I can figure him out. He's 4 times 5 minus 1. 5 minus 1 is 4. That's a 16. Oh, then I just got to subtract 16 over and divide by 3. Oh, let's see. 34 minus 16. 18. Then divide both sides by 3. Ta-da! Ooh, that was good. I like that one. I like that one. So you're just using your properties. So if I have an integral of 2 separate things, I can integral them separately. And if it's a constant of a 3, I can pop him out front. And then I got to remember this guy. He's a constant, so he's 4 times the width. And then I just solved it. This is the guy I want. Just went algebra on it. Okay, so now let's talk even and odd functions. So if you're an even function, if I was going from 0 to 3 of f of x dx and I get that it's 8 and it's an even function, now remember even function means that it is symmetrical on the y-axis. Then what is the value from -3 to 3? Well, the answer there would be 16. Here's why. Let's look at the graph y equals x squared. P is an even function because he has symmetry on the y-axis. So if I'm looking at the area under the curve from 0 to 3, and you're telling me that that's 8, then from -3 to 0 should be the same amount of area. And I know I didn't draw that even, but you get the picture. This area on the right should be the same as the area on the left. So if it's even, then it should be double. If it's an odd function, and my favorite odd function is y equals x cubed, which does that, but a little bit better than I drew it. All right, so from 0 to 3, so if that area is an 8, then from -3 to 0 should be the same amount of area, but it should be negative. So the total area should be a 0. In some cases, a definite integral can be evaluated by using geometry. All right, so this should go very quick and we're almost done. So this is linear. I want the area under the curve x plus 3 from 1 to 4. Well, 1, 2, 3, and a slope of 1. I mean, you should be able to draw this like super fast. And I want the area from 1 to 4. So I want this. Well, that's a trap. No, I do that every time. 1/2 height, base 1 plus base 2. So 1/2, now the height on this one it's this way. So that's a 3. And then my uneven are my bases. So however it's turned, your 2 uneven pieces are your bases. The height is the same all the way through it until you hit that angle. So he is 1, 2, 3, 4. And then at 4, I can plug a 4 in there and get a 7. So 3 over 2 times 11, so 33 over 2. Units squared, because technically it's area. Okay, this guy, oh, that's that cute semicircle. Radius 2. I'm going from -2 to 2. Well, you just got to know that that's half a circle. So pi r squared over 2. Radius is 2, so that'd be 4 pi over 2, 2 pi. All right, home stretch. Oh boy. Absolute value of x plus 3. That shifts it up 3. And I want to go from -2 to 4. Pause it, draw it, make it pretty. So I see 2 traps. I see one on this side and one on this side. So 1/2. All right, the base or the height, whichever, is the, okay, so that's going to be 2. And then I need that height and that height. So, and that's at 0 and at -2. So I can just plug those in. So 0 would be a 3 and -2 would be a 5. So 8. And then I got to do it again. 1/2. All right, that's a 4. And then his height is a 3. All right, and that's a 4, so that'd be a 7. So 2 times 10, that's a 20. So 28. And again, if I'm going too fast, pause it. Let it digest. The cubed root of x. All right, the cube root of x, and I don't think there's any reason you should have what this looks like memorized, but he is the inverse function of x cubed. So you know how x cubed does this? So this guy does this. And again, not sure they can expect you to have that guy memorized, so you could graph him. And I want to go from -4 to 4. That's definitely going to be a big fat 0 because I know I didn't draw it right, but he is symmetrical. And think about it, x cubed has y-axis symmetry, so the cube root of x is going to have x-axis symmetry. So anyway, same amount of area under here, same amount of area above there. And I'm going from -4 to 4, so it's the same. All right. Okay, tell you what, pause me. Pause me and try this one on your own, so you can go at your own pace. Up 2, up 3, right 1. And I'm going from 1 to 4. So I want all of that. So trapezoid. 1, 2, 3. Yeah. And let's see, his height at 1, I'm just going to plug a 1 in. It's going to give me a 5 and plug a 4 in. 12, 14. So 19, 3 over 2, I don't know what that is, 51 over 2. No, 57, gosh, 3 times 9 is 27, sorry, 57 over 2, not 51. Okay, F. Oh boy. So we're going to look at these two separately, and I'm going to live in denial about the first one. I'm going to go to the second one. So this one is, let's see, y-intercept of 3, down 1, right 1, and I'm going from 2, I don't know where he crosses. I'm going from 2 to 5. Yeah, 2 to 5. Okay, so looks triangular. So 1/2, let's see, base is 3, and let's see, at 2, this is at, actually it's not at 0, it's at 1. And at 5, it's down here at -2. So if he's at 1 and -2, then his height is 3. So 9 over 2. I should have drawn that better. Let me draw that better for y'all. One, two, three. Down 1, right 1. Down 1, right 1. Down 1, right 1. Okay. And I'm going from 2. Oh, part of it's positive. See? And 1, 2, 3, 4, 5. Ooh, okay, I got to do this as 2 separate. Ooh, I'm glad I did that. Okay, so he's got a little triangle above sea level, so 1/2, width is 1, height is 1. So he's got a positive 1/2 area, and then when I look at that area, base is 2, and at 5 we said he's at -2, right? Because 3 minus 5. So his height is 2, 4, so that's 2, but it's negative because it's below sea level. So -3 over 2. Okay. I like that. Yeah. Okay, let's look at this guy. I am gonna, yep, I'm gonna separate this. Instead of looking at this as a semicircle that gets jacked up 1, I'm gonna do this. And I guess I could have done that with the other one. Like I could have done from 2 to 5 of 3, and then minus from 2 to 5 of x, and done them separately. That would have probably been a lot easier. You know, live and learn. This one is super easy because it's 1 times 2 minus 0, which is 2. Okay, so he's a 2. This one is my semicircle, and I only want from 0 to 2, so that's a quarter circle. So pi r squared over 4. R is 2. 2 squared is 4, so that's just pi. Okay, so now I have, that's a -1.5 and a 2, so I have 1/2 plus pi. Woo! That's a doozy. Make sure you understand about the pulling it apart. So like for the first part of F, I pulled it apart. Second part, I did not, but you could have. And that would have prevented us from having a triangle above and a triangle below. So that would have been, if you guys want to see it, if you don't, you can fast forward. You could have done 3, 5 minus 2 is 3, so that would have been a 9. Then this one, and I'm going from 2 to 5, trapezoid, so 1/2, base is 3. That height, remember your function is just an x. When you plug in a 2, you're going to get a 2. Plug in a 5, you're going to get a 5. 7 times 3, 21 over 2. Remember, it's a minus. And that would be 18 over 2. And 18 over 2 minus 21 over 2 is a -3 over 2. which is what we got. So either way. All right. I've been saying home stretch for forever. Almost done. This is it. Last 4, 3, 4, 3. All right, here we go. We can do it. What about functions you don't know how to integrate? So for this one, I'm going to think about the graph. Absolute value shifted right 4. And I'm going from 0 to 6. So I want all this area. So 1/2 base. That's a 4. Height at 0 would be a 4. And then let me do this triangle. So 1/2 his base is 2. And then at 6, his height is going to be a 2. 16, half of 16 is 8. 4, half of 4 is 2. Area is 10. This guy, I feel like we did this. He's the half circle, 2 to 2, or negative 2 to 2. He is radius 2 because there's a 4 right there. So pi r squared over 2 because it's a half a circle. So radius here is a 2, so that would be a 4. 4 pi over 2 is 2 pi, so his area is 2 pi. I feel like we just did that one. Oh, we did. A page ago. All right. Okay, speaking of graphs. Oh my, that's pretty. The graph of the function f shown to the left consists of 3 quarter circles. Which of the following is or are equivalent to the area from 0 to 2? So the area from 0 to 2. So first of all, that would be positive. Okay. All right. So now it wants to know who is going to be equivalent to that area. So this says 1/2 from negative 2 to 2. So negative 2 to 2 would all be positive, and it would look to be double. So yes, I like that one. Because here's the area from negative 2 to 2. So if I go, from 0 to 2. If I go from negative 2 to 2, it would double that area. So if we halved it, yes, absolutely. So I like 1. So those 2 are out. Okay, now it wants from 4. From 4 to 2. Okay, so that's backwards. So from 4 to 2. That's backwards, so it needs to be negative. But it's also below the x-axis, so that's negative, and a double negative would make it a positive. So then this would match this. So that's true. I'm going to do that again. This is from 4 to 2, which is backwards. So negative area because I'm rolling this way. It is also an area that is below sea level, so it's a negative area to start with. So when I go backwards on a negative area, that's going to make it positive. So I like 2. All right, now we need to decide on 3. Let me erase. Start with a clean slate. Okay, I'm going from 0 to 4, and I want to half it. 0 to 4. That would be positive. That would be negative. They would cancel out and give me 0. Half of 0 would give me 0. So no, absolutely not. So I like that one. Whew, that was a lot. So yeah, make sure you're good. I know I went fast through some of the shapes, but again, I did that because I know that you can pause it and go at your own pace. So I hope you start anything that you have any serious questions about. If you have little questions, I strongly hope that you're going to go back and re-listen to some of those examples. But this is kind of laying the foundation for your house of integrals, so it's very important.